Hey everybody, let's continue our discussion about oscillations. Let's go back to our mass bouncing on the spring. So you have a mass connected to a spring, and let's say this is the x direction, and you pull the block over here, and then it just bounces back and forth. And then there was some second order ODE governing that motion that looked like this. Right, this second order ODE, which you know how to solve, right? The solution looks like this, some kind of sinusoid for amplitude here, angular frequency here, phase angle here. Okay, but what if the spring were vertical? Like if the mass were hanging, or maybe more generically, like it's a ramp, and then there's a spring, then the mass is over here, and this is at some angle. So let's say the angle is 90 degrees, then it's kind of like this. So maybe this is more generic a picture. Let's say this is smooth. Okay, so what's that free body diagram? There's spring force over here, normal force, weight. Let me pick coordinates. Let's see, the angle would be right over here. Okay, so in the x direction, we got mg sine minus spring force equals mass times acceleration. Okay, so let me just let me move this on that side of the equation. Okay, we can divide everything by something that's non-zero, the mass. I'll just divide everything by mass. Okay, and then acceleration is the second derivative of position. Okay, now take a look at this, our second order ODE, compared to this. The difference is right here, right? Otherwise it'd be the same. So this is called a homogeneous second order ODE because it's zero over here. This is not zero, so this is a inhomogeneous second order ODE. So how do you deal with that? It'd be nice if we could just get rid of that. So here's a trick. Because this is constant, here's a trick I'll show you. Let's move this back on this side of the equation. So I'll start writing over here. Okay, so I'll move this on the other side, so on this side. Okay, and you see how this is k over m? I'm gonna write it like this. Right? K over m, m over k. I mean, that's 1, right? You can always multiply something by 1. But now, see how they have a common factor? I'll rewrite this on another line. So I can factor out k over m. Right? Same thing. Same thing. So this is the same thing as this. But the trick, I can do a substitution. Let's say u substitution equals this whole thing. And then what's the derivative? The derivative of a constant is 0. Right? And then same, like do you do another derivative? These are the same. So this is here. Okay, so then this is u. And now look, here let me just keep everything. This turned into this. Okay, and you know how to solve something that looks like this. Right? It is now a homogeneous second order ODE. Right, take a look at this, take a look at this. Just by doing our clever trick with this U substitution. So you would know the answer. The answer would be some kind of sinusoid. Right? But that's not x. We wanted the solution in terms of x. So see our substitution? Just change it back. X would be U, and then see, just move this back on the other side, plus whatever that was. And there we go. This is the solution for this inhomogeneous second order ODE. Here. Okay, right here. So remember that trick. It's pretty useful. Okay, so let me know if you have any questions. See you on the next video.